So yeah, once you do that, it's a walk in the park. So let's go forward. Weird. There's something in the fall. Okay, so let's go back to writing mode. Boom. Okay, wait, something's wrong with this. This is not what I want. There we go. Okay, so let's scroll down. Take a scroll. So last class we talked about, oh yeah, pumping, right? How much work does it take to pump water? And we had this whole idea that, you know, you had the straw, and you could think of your cylinder as like split up into pieces, right? That's why I've got those little hockey pucks. And you can imagine yourself like sucking out one hockey puck at a time, right? And so we calculated the amount of work to suck out one of those hockey pucks. And then we realized, like, okay, well, if you want to calculate the work to suck out one of those hockey pucks, you first need to calculate the volume of said hockey puck. So we did that. It was like delta x tall, then it was like pi r squared times delta x. And then once you have the volume, well, you can multiply by a constant depending upon whatever liquid you're dealing with is. So the force required to suck the liquid will be the volume times some density. Yeah, density, my bad. So then once you've got your force equation, you can multiply that by the distance that you'll have to suck it, and then that will give you the work. And then obviously, so the thing is, like in my little drawing right here, like as you start sucking the water, there's less distance that you have to move it from the top, right? And then like basically as you suck the water, your straw has to go down, right? Thereby meaning that you have to suck it more and more and more. And like there was a good, this has like some interesting applications. I talked about like fracking, right? Like that's like one of the issues with fracking. Like you're drilling oil, right? And you're basically sucking it out of the ground, right? The deeper down it goes, the harder it is to get. And like as a civilization, we're dealing with that problem right now, right? Like we've sucked up all the easy to get to oil, right? So now like what are we having to do? We like make these straws into the ground, and then we make another straw that goes into the ground, and one straw we're going like blowing into it, so hoping that it makes the oil come up while we suck from the other end. Like that's why fracking is so what's it called? So expensive compared to other things where it's like all you need to do is suck out the oil. This requires like extra pressure to get it moving. Does anyone know how it works? Like they pump like heated water into the oil to heat it up to make it easier to suck out, right? Like it's like really cool. Once you take like a physics class, you start realizing why fracking like has such a low return or negative return even on investment. Because it's like some idiot who never took a physics class was like, yeah, this is what I'm gonna do. Yeah, and it screws up the ground terribly, so it just ends up not really being worth it, which is why like fracking is sort of just slowly going away. Okay, so anyway, so we did this. Then we did another example with sucking up a cone. It's the same whole idea. You imagine little hockey pucks. Okay, so let's keep going forward. Today, we're going to talk about, still like water, but not pumping water. We're going to talk about hydrostatic force and pressure. Okay. So we're going to talk about, like, first of all, what's the difference between force and pressure? It's good to know. So remember that force equals mass times acceleration. It's what you need to do to move something. Right, yeah. So we're going to go into that. So force is like the force applied to move something. To move or to accelerate. So the whole idea is that you are accelerating an object of mass m. Now, pressure is force per unit area. So very close to what Kabir said. So pressure equals the force divided by the area. And we can give you a good example of why you should think about this. Say here's the ground. Everyone see the little lines, like there's the ground. And let's say there's this big cube, like on the ground. It's like huge. It's like the size of a person. Okay, and then here's you. And does it make sense that you are pushing the cube with some force F? Okay. Now, where does this force make contact with the cube? Yeah, with wherever your hands are. So let's say that you have ideally when you push something, you want to open your hands, right? If you start pushing really hard. Because let's say that you decide to use one finger, and I'm going to use my middle finger, so like I'm flicking it off. If you try to push an object by only pressing with your middle fingers, what's going to happen if you go like full force with like 2 fingers like this? Yeah, by fingers. Because the pressure has changed. The force could be the same. So if here are your hands, that's some area, I don't know, let's just say 5 square units. But if all you do is press with so let's say the object is right here. Unless you're like those monks who like trained their fingers like that. So like here's like your middle fingers pointing out, and notice that they only touch like right there and right there, right? Whereas your hands, they're touching across the whole area. So let's say that the area would be 1 unit squared. So notice, even though the force applied is the same, the pressure will be higher because, in the case of your little fingers only doing it, because only your fingers are applying the same force, right? It's like, has anyone ever seen the cool like science things where apparently there's police activity on campus right now. Did anyone else get that alert? Yeah. Well, thoughts and prayers. Continuing on to math. It like threw me off. I was like, what the hell's going on? So has anyone ever seen like those things where it's like the bed of nails? Like maybe you went to one of those physics shows. So, yeah, it's the same exact idea. You lay down on the bed of nails, and the pressure is lower because you're spreading the weight over a larger area, as opposed to if there was one nail and then you like tried to lay down on it. Does everyone see like my the one red nail, and like the person's like, let me try to like lay down on this nail, right? The whole force of your body is going down on that one little point as opposed to the whole thing. So it's the same exact idea. Okay. So we're going to talk about like calculating pressures and stuff like this. And actually, let's talk about the units. So force is mass times acceleration, which is kilograms times meters per second squared, right? And what is the kilogram meter per second squared called? Let's remind ourselves. What's like the kilogram times meter per second squared? Like this has a special name. The unit of force. The Newton, yes, cool. So the Newton is the kilogram per meter squared. Okay, now pressure is force per area. Now your force is kilogram meters per second squared. And your area is meters squared. So if you go and you simplify that, you get kilogram meters per second squared times 1 over square meters. So that gives you the kilogram per meter second squared. Yes. Okay, and this has a special name. It's called the Pascal. It's the newtons per square meter. named after Blaise Pascal, I believe. So newtons per square meter are called pascals. Or if you just want it in terms of units, it's the kilogram per meter squared. Kilograms per meter times second squared. Bleh. Okay, so we have these pascals. In the metric system, what do we call? How do we measure pressure? So metric is pascals. What's the measure of pressure in the imperial system? Just because we use it a lot. Yeah, PSI. The pounds per square inch, and that makes sense because pound is a measure of force, square inches are a measure of area, right? And pressure is force over area. Okay. So to start talking about this, we're going to imagine you've got like a pool. There's my pool. Okay, and let's say that like what you do is you just put a disc down at the bottom of the pool. Okay, so if you think about this disc down at the bottom of the pool, there is a force being applied down onto it. What is it that is determining the force being applied onto this? Like, what is the cause of said force on this disc? The water being, gravity. Gravity is pulling the water down onto the disc, right? Gravity is accelerating the mass of the water onto the disc. So the force is a product of the interaction of gravity and water, right? Cool. So does it make sense that when you submerge things, there are forces on them, right? Due to the weight of the gravity. I'm sorry, the weight of the water. The weight of gravity. That made no sense. I mean, the weight of the mass, or the force of the mass, due to the acceleration of gravity. There we go. Okay, now this force gets applied. So actually, if you think about it, like all of the water above this disc, like brings its weight down onto the disc. So you have this. So now you can figure out that there's actually a pressure here, right? The pressure is going to be the force divided by the area of the disc. Right? Cool so far? So you have the pressure exerted by the water on the submerged object, right? You divide the force by the area. We call this hydrostatic pressure. It's called hydrostatic because it comes from the water. And why do you think it's called static? Why is it hydrostatic pressure? Yes, very close. It's not changing because the water is still. If you start having waves in your pool and the water is no longer still, if there's like currents, you have to take into account the different forces. Does that make sense? Like what we're talking about here only makes sense if you talk about still water. Okay, everything gets more complicated once you start adding movement in. So we're calculating the force due to just like the water existing, assuming it's like not moving. Okay, cool. And interesting fact. So let's say you have your disk. And your disk is like this, or your disk is like this. The force on this disk and the force on this disk, are they the same? Are they different? Is there only force from the water if like the disk is like if the face of the disc is pointing up, is it different if the disc is like pointed sideways? It's an interesting question. What do we think? Like if you change the orientation of the disc, does that like change how the water is exerting force onto the disc? No, the area is the same. The area stays the same, and the force is the same, because like otherwise, if you submerged a submarine, if you rotated it a particular way, it can no longer be crushed by the water. So this is called Pascal's principle. I mean, like no matter what direction the force is coming from, the force remains constant. This is like an important thing to keep track of. So what's it called? Pascal's principle says that the hydrostatic force is constant at clicking around. I need to like rearrange my stuff on my desk. It's like making me go insane. So Pascal's principle says that hydrostatic force is constant at a given depth. The orientation changes nothing. Otherwise, what you could do is like turn your submarine, right? And all of a sudden it would no longer be crushed by the great weight of the sea. Okay. So like, what we're interested in is like calculating like, okay, like you have your pool. You know, like draw like a little pool here. Does everyone see my beautiful pool, how like it like slopes? It like gets deeper. So like you can figure out like, hey, how much pressure is exerted right here on the edge of the pool? How much pressure is exerted right here on the edge of the pool? How much pressure is exerted at the bottom of the pool? So the deeper down you go, what's going to happen to the pressure? Like it will increase, right? Because there's more water bearing down upon it. So we're gonna talk about that. So if you were in the business of like making submarines, like you'd want to be able to calculate this stuff. Okay. So, let's do a calculation. So, let's say here's the surface of the water. Okay, and then you can just like imagine. Keeps going down forever. And here is let's draw our little plate or disc. So there's our little plate. Okay. And so X is going to be how submerged the object is. So X is depth. So does it make sense at the surface, X equals 0? So let's say the top of the circle is at X equals A. The bottom of the circle is at X equals B. Okay, now, what's annoying about this? If you want to calculate pressure, like you could look at the pressure, say, in this section of the disk. But you could also look at the pressure of this section of the disk. Why are we sad now? Like, what's really annoying about this? Well, no, that would be annoying. But like, if you needed to calculate something, what can you say about the pressure on this part and the pressure on this part? It'll be greater on the bottom, right? They're not the same, right? This is like the same problem we encountered with pumping water, right? The more you pump the water, the deeper you have to go. The deeper you go, in this case, the more hydrostatic pressure there is, right? So does it make sense if you have a really big object, the amount of pressure that it encounters at the top is less than the amount of pressure that it encounters at the bottom. So like you can actually imagine, so what do you think would happen if you took like a big, huge cylinder that was like a mile long and you submerged it? Like what might, and like let's say it's hollow. Like what might be really weird that's gonna happen to this thing? Like you have this like metal cylinder and you submerge it down. Like as you keep on submerging it, what's gonna happen to it? Yeah, the bottom will collapse, right? Yeah, like because the force increases the deeper you go, right? So does it make sense? Like this part might be completely crushed, but up at the top you're like, everything's fine. Like there's nothing wrong with this. Right, so this is why you might care about these sorts of things. If you think about it, you know how like they sink, this goes back to oil. Like when you want to get oil out in the ocean, what's our tool for getting oil in the ocean? There's this big thing that we put out there. Yeah, exactly. Does it make sense? The oil rig has these like things that get submerged and they have these pipes that go down to the bottom of the ocean floor. Imagine the pipes have to be designed so that they can take the forces at the bottom, not the forces at the top. And so you actually have to calculate all this shit. Unfortunately, a lot of the applications that I know of about these things apply to things like in the military, like building rockets, or petroleum engineering, and stuff like that. All jobs that are probably going to be disappearing, so I apologize for my untimely examples, but I think that they illustrate the engineering practicality of this. I don't know if anyone got that joke or not. Okay. So, what are we going to do? If we want to figure out the total pressure on this, what is our method for doing stuff? Like if we want to figure out the total pressure exerted on this disk, what has been our go-to for calculating stuff like this? Right, but like there's a step to get there. Yeah, pressure of 4 parts, exactly. So you say like, let's just break it up into 4 parts, calculate them each individually, and then like let's then add it to it, and then you're like, okay, I see what the 4 parts look like. Let's do it for adding up n parts, and then you're like, okay, cool. Now let's take the limit of that, and then you turn that into an integral, and you're like, hey, problem solved, and the crowd goes wild. So let's do that. So we're gonna break this up into 4 parts. Right, from A to B, you get your x0, x1. x2, x3, x4. Okay, so you're going to get like this. Right, so you get your 4 regions. You get the region for this one, this region, this region, that region. Okay, how tall are each of these regions? So if you look at these like little 4 regions, how tall are they? Yeah, or just delta x, yeah. So that thing is delta x tall, delta x tall, delta x tall, delta x tall. Now, if you want to calculate the pressure for, say, this one right here, your pressure, your PI, is going to be equal to the force that it encounters over the area. Okay, which means we need to, do some calculations. So, the force is going to be dependent upon the depth, right? Actually, wait. Let me make this a little easier for us. Oh, okay. Yeah, so let's make some simplifying assumptions here. So let's not do pressure first. Let's talk about force first. So the force for this little part right here depends upon what things? The depth of the object and the weight of the water, right? Or the amount of water. Actually, wait. No, it just depends upon the depth. Oh, dang. Wait. I'm like missing a detail here. 1 second. Wait a second. Feel it. Well, not the mass of the mass of the water matters, but that's dependent upon the depth. Oh, okay. No wonder. I was missing a formula here. Okay, we have a nice formula to do this. My bad. So the formula that we're going to use when we calculate this is that the force depends upon rho A x, where rho is dependent, or rho is the density of your liquid or whatever you're dealing with. Your A is the area of your object, and X is the depth. There we go. I was like, I'm like missing something here. So if you look at this little section, the one that we're dealing with, it looks pretty close to a rectangle, right? So the force exerted on it is equal to whatever my density of my liquid is, let's not care about that right now, times the area of the thing I'm dealing with. So the area of that thing I'm dealing with, it's going to have some width times some height. So let's just say it has some width. So Wx star is just going to give me my width. It's my width function. And then what's the height of that little thing? Delta x. And usually what you want to do is, what does x star usually stand for? We've usually used this for something. Like x1 is right here. Yeah, x2 is right here. Yeah, x star is usually the midpoint. So normally what you end up doing is you just say like, well, how wide is it at the midpoint right here? Okay, so that gives you the area of that little rectangle. You get the width times the height, and then you multiply by x, where x is the depth. Oh. Okay, so that's one of the forces on those things. So if you add up the force, you get your approximate force. So let's say F equals the sum of all of these. Now, what do you do? Okay, wait. Oh, yeah. Okay, so you got your force. That would be the approximation. You would take the limit of it to get your integral. So you'll integrate your force function. And then how do you actually get pressure? So if you want pressure, yeah, you divide by the total area. So this becomes the integral from A to B, and then here's the thing that I have to integrate. I'm going to have my density times my width function times x dx. Okay, and that gives you your force. And then if you want pressure, you're just going to take that integral and divide by the area. Boom. Or this is just what you could do to find the force on the object. Okay, so it's like what we've been doing before. So let's do an example of this so you can like see it all worked out. You can sort of see like why. Oh, why 4 parts? Because it's just easy to draw 4 parts as an example. It's just like, I recommend when you draw your diagram, because you can't draw an arbitrary number of parts, I like to draw 4. Just know that like, you could draw any number you want. Someone, just for the person who messaged me, like there's no particular reason why you need to draw 4. Eventually you let n go to infinity, right? The number of parts go to infinity. So it's just nice to be able to see some of them. Alright, so let's say that you have a water trough, like that animals drink out of. Or I don't know. You have like, fact is you have like a pool, a trough, a something. So I'm gonna draw it. Okay, does everyone see like my weird trough? Like what it is you can imagine an isosceles triangle, and that's what it looks like from the side. Right? So it's like it's really open wide at the top and then it funnels down. So let me draw the sides. Yeah, it's like a prism. And there's the bottom. Okay. So what we're wondering, so let's say that, let's add some dimensions here. The trough is 15 feet long. And if you look at one of those isosceles triangle sides, okay, so like this is that side right there, or that side right there. Let's say that it is 8 wide on the top, and it's going to have a height of 3. Okay, cool. Okay, so let's assume the trough is full of water. How much force is the water exerting on one end of the trough? So in other words, like if you were to look at this end over here in green, I'm gonna like fill it in.
I'm gonna go to the end with a few friends.
Alright, is school over?
Yeah.
Right now? Oh, wait, it's Wednesday, you end early, right?
Yeah.
Okay. Okay. So you have this like side of the water, I'm sorry, the side of the trough, and the water is pushing up against that, right? Now, if you don't do a very good job of like welding right here in red, where it connects on the sides, what's going to happen to your trough? Like, does it make sense you'd have to weld that? Right, it's going to burst, right? So does it make sense that like when you make troughs or something that holds liquid, you need to figure out how much pressure is going on one of the sides? Otherwise, like, it could burst, right? Does it make? I just want to like see, like, does that idea make sense? Like, why, if you're going to be building stuff, like, you need to be able to figure out how much force like your welds are going to have to withstand. Usually, when you build objects that contain water, do you put straight edges on them? Like, if you think about it, if you look at like big structures that hold water, do they ever like put two plates together? Like, is that a good idea? Yeah, exactly. Does anyone know why you use the curve? Like, you hold it like in a sphere or something like that, or like you have like a curved cylinder? Does anyone know why you have the curves and no joints? Yeah, the pressure is evenly distributed and it makes life a lot easier. The hard part is making those things. So back in the day when, you know, it was hard to make like curved pieces of metal, like, they'd have to do this. They'd be like, oh shit, how strong is this goddamn weld gonna have to be? And they'd have to like reinforce the edges. So anyways, like, we're gonna imagine that's us now. So we're gonna calculate like, well, how much force does this weld need to be able to withstand? Because the thing is gonna be pushed by the force of the liquid. Okay, so we draw our thing. Okay, so let's draw it into 4 equal pieces. Okay, x is the amount that it's submerged. So what's x at the bottom? What's the most that you can be submerged? 3, nice. Okay, so you have the force that the water exerts on this top piece. And then you have the force that the water exerts on this piece. And then you have the force that the water exerts on that piece. And then you've got the force that the water exerts on this piece. Let's use, and then how tall are all of them? Delta x, right? And I'm going to look at this one right here to do my calculation. So remember, the force applied on your little segment is equal to the density of your liquid times the width at the midpoint times the depth. That gives you the area. Oh shit. The width times the height, my bad, which is delta x, times the depth. There we go. Let's say depth at the midpoint. Okay. So we'll just leave rho as rho. Now we need to figure out how wide you are at delta x. So, I'm sorry, you need to figure out how wide we are at x star. Damn, I'm so sorry. I'm just like saying like ridiculous shit. So let's imagine right here in the midpoint, that midpoint is at some depth x star. Okay, right? Everyone sees the rectangle. The rectangle has a midpoint. We want to know how deep down that midpoint is. That's x star. So I'm just going to draw part of this isosceles triangle. Okay, at the top it is 4, right? Does it make sense this space is 4 because I'm drawing half of the isosceles triangle? The side is length 3. And then I'm interested at what happens right here. Okay, so where do I put x star? What is x star measuring in this new triangle? So like, where do I put x star on this diagram? Right here, and then this part will be 3 minus x star, right? Because x star is the depth, so it's the height of this thing, and it splits it up into two parts, right? Okay, so we want to know how wide this thing is here, so this is going to be 1/2 w. Okay, and then we can set up similar triangles. We know that 4 divided by 3 is equal to 1/2 w divided by 3 minus x star. So if you multiply, you get 4 times 3 minus x star equals 3 times 1/2 w. So if you multiply both sides by 2/3, you get what your w function is. So how wide are we? It is 8/3 times 3 minus x star. So if you want to know how wide that rectangle is, you enter in the depth of the midpoint x star, 3 minus that times x thirds, give x. Sorry, if you want to know how wide that is at the depth x star, you take x star, 3 minus x star times 8/3 is how wide that rectangle is. Okay, so now we can plug that into the force equation. So you get your density times 8/3, 3 minus x star. That's going to be multiplied by delta x multiplied by x star. So that's your force. Now, what would you do? Well, you're going to sum all these forces and then take the limit of that sum. That gives you a Riemann sum. So the force exerted on it will be equal to the integral. You're going to go from a height of 0 to a height of 3. And you're going to integrate rho 8/3 3 minus x times x dx, right? The delta x becomes dx in the integral, so I just moved it. So you would integrate this, and that would give you your total force. I talked about this before because we're dealing in feet. Assume all this is feet. The density of water in the imperial system is 62.4, so that would be given to you in the problem. So we would be integrating 0 to 3, 62.4. Let's distribute that 8/3. 8/3 times 3 will be 8. 8/3 times x will be 8/3 x. We'll multiply that by x dx, which will give us, let's factor out the 62.4, integrate from 0 to 3. Now we have to multiply x into everything. So you get 8x minus 8/3 x squared dx. Okay, so you can find an antiderivative for that. The antiderivative will be 4x squared minus 8x cubed. Okay, so now you need to plug 3 and 0 into that. You'll get 4 times 3 squared minus 8 times 3 cubed, which would be 4 times 9, which is 36. 8 times 27 is 75 plus 6, which will be 81. Oh man, so you get a negative number? guess so. Yeah. Did I do like multiplication there wrong? Yeah, we're plugging in 3. What's 36 minus 81? I feel unable to do that in my head. Thank you. I was like on a roll and then I like ground to a halt there. It was actually so sad. I felt like I was on fire and then I was like, oh shit, I do not want to subtract. So what happens when you plug 0 into this thing? You just get 0. Wait, we're not supposed to get a negative number. What is 62.4 times negative 45? No, because it's going to be f of 3 minus f of 0. Right? So you get negative 45 minus 0. Can someone tell me, though, what's 62.4 times 45? Okay, so I made a mistake somewhere. What did I screw up? Okay, I screwed up. I know everything's good. I know that the integral's set up right. I think I screwed up the antiderivative. What is the derivative of 8x cubed? Oh shit, yeah. I screwed up the antiderivative, that was the problem. It's 4x squared minus 9/4 x cubed. Wait. No. That's not right. Okay, let's just write it out. We're gonna have 8/3, and then we're gonna get 1/3 x to the third. It's gonna be 8/9 x cubed. There we go. My bad. Okay, so that rechanges our f of 3 calculation. We'll get 4 times 3 squared minus 8/9 3 cubed, which is still 4 times 9, which is 36, but now we get minus 8 times 9 times 27. And what's 27 divided by 9? 3. Yeah, and 8 times 3 is 24. Yes, and 36 minus 24 is... 36 minus 24 is... crap. 12? 36 minus 24? Yeah, okay, cool. Yay! Positive number. So you get 62.4 times 12, and what's that? There we go, that actually makes sense. Cool, I'm gonna answer this, I'm gonna just talk about what this number means, and I'm gonna answer Sid's question afterwards. So apparently, how many pounds of pressure, what's the force? 748.8 pounds. So actually, that's pretty intense. This little trough you have going on here, on that one end, it has to be able to withstand 748.8 pounds of force on those welds. Okay, so now Sid asked, so when we set up the Riemann sum for these types of problems, do the integral limits show up anywhere in the sum? Yeah, the integral limits... Oh, do they show up in the sum, or they only come into play once we actually set up the integral itself? They really only come into play when you set up the integral itself, the 0 and 3. You have to remember that x equals depth, right? So you have to integrate over the depth, right? So the depth goes from the top of the trough at 0 all the way down to the bottom of the trough at 3. They, like you said, those numbers do not show up anywhere in my... I didn't do the Riemann sum here, but I did the formula for the Riemann sum, right? I had this stuff. Normally I would have said, well, what's the total force? It would be the sum of those FIs. But yeah, those limits of integration don't show up anywhere in the Riemann sum. Yeah, that comes from the trough. So here's the picture of the trough. So x is the depth. So you start off at the top of the trough at x equals 0, and you end up all the forces at the bottom of the trough at x equals 3. So you're basically accumulating the force as you go. You say, like, how much force do I have on this segment? How much force do I have on that segment? How much force do I have on that segment? And you keep going. Because the depth of the trough is 3, it's 4 wide. You're going down, you're not going sideways. Very, very common mistake. Also, it's not easy when you're tired. Everyone was able to sort of see me fall apart at the end there, right? With the calculations. I was like, no! I lost it! Luckily, I just made one mistake, and it wasn't like a complete bust. But these problems, like, it's a lot, right? There's like a lot going on. You have to draw the picture. You have to, like, I highly recommend that you draw that thing where you have like the 4 little segments. You know, it really helps when you draw the segments because, like what Alina asked, you realize that you're integrating down going like this, because that's where your x0, your x1, your x2, your x3, and your x4 were. You're going down like that. No, that makes no difference. Practically, though, for some physics problems, yes, if you weren't able to find an antiderivative and you needed to use numerical methods to calculate this stuff, a lot of the times using the midpoint has a variety of positives compared to using the edges to do the calculations, though. Does that sort of make sense? Like, for most of the stuff that we deal with, it doesn't really matter, but yeah, if you actually have to start doing this stuff in real life, it would make a difference. Yeah, it is a good rule of thumb to use the x star with the midpoint. Okay. We're done, right? Yeah, we're done. Hot dog. Okay. I'm gonna end the recording.